Hello and welcome to EPG Pathshala. This module is on growth of literature. In this module, we shall look at the characteristics of growth, different models that are used to explain growth phenomena, classification of growth models, and obsolescence of growth literature. Growth characteristics. The number of scientific journals, including the abstracting periodicals, are simple indicators of scientific growth. Scientific literature grows exponentially, and on an average, it is growing at the rate of 5% per year. We may observe that there are many items in science that grow exponentially. Growth of publications, the four stages. Derek de Solla Price suggested that growth of publications pass through four stages. According to him, Michael Mabe and many others, the four stages are preliminary period of growth, period of exponential growth, period in which the rate of growth declines, and finally, the period in which absolute increase declines. The S-shaped curve reveals these four stages. In the above curve, there are four stages: concave shape, straight line upward, convex, and then a curve close to a horizontal line. This is very clear in figure 1 that you see. He estimated the number of the scholarly periodical titles being published by the end of 20th century would exceed 1 million. Growth rate of journals. Michael Mabe observed that journal growth rates have been remarkably consistent over time, with average growth rates of 3.46% since 1800. He further observed, in the period from 1900 to 1940, the number of active journal titles grew at an actual rate of 3.23%, a doubling time of 22 years. In the period from 1945 to 1976, the number of journals grew at an annual rate of 4.35%, representing a doubling time of 16 years. And since 1977, the number of journals grew at 3.26%. Slow growth rates after the mid 1970s were perhaps due to the oil crisis of the 1970s, the increasing public awareness of potential ecological disaster, and the turning away from nuclear technology in the 1950s. Statisticians have identified several models to explain the growth phenomena. Five well-known models are the exponential model, the logistic model, the Gompertz model, the power model, Ware's model. Depending on certain situations or the assumptions, we may have to choose a model to explain the data that we have. According to Thomas Robert Malthus, any species can potentially increase in numbers according to a geometric series. It represents an increase with a fixed proportion of total population for each unit of time. It involves a constant ratio of change. For example, if a species has non-overlapping populations, say annual plants, and each organism produces B offspring, then population numbers A in generations T is equal to 0, 1, 2, 3 is given by y to the base t is equal to ab to the power t. In this case, the growth rate is p minus 1 into 100. Log linear model is expressed as log y is equal to log alpha plus beta x. Here, beta is the slope of the curve and measures proportional changes in y for a given absolute change in x. The exponential function assumes a convex shape in this graphical presentation. The increase is proportional to the size, that is, if the population is y at time t, then 1 by y dy by dx is equal to beta. The exponential mode can be applied to both growth process and decay process. Suppose the growth rate is proportional to the produce of the present size and the future amount of growth, and with alpha as limiting growth value, then we have, for k being greater than 0, dy by dt is equal to ky alpha minus y divided by alpha. That is, the growth rate is relative to present size, which is dw divided by y dt. That declines linearly with increasing y. Integrating the above equation, we have y is equal to alpha divided by 1 plus beta e to the power minus kt. This is known as the logistic model. A simple version is also represented as y is equal to a divided by bc to the power t. Sometimes it is also represented as 1 divided by k plus bc to the power t. The logistic curve has an S shape. For t minus 0, y is equal to alpha divided by 1 plus beta, so that this is the starting growth value. For t is equal to infinity, y is equal to alpha, the limiting growth value. It also follows beta k is greater than 0. If the growth rate is dy divided by dt is equal to ky log alpha divided by y, then the Gompertz model is defined as y is equal to alpha exponent minus beta e to the power minus kt. The curve is S-shaped like logistic. However, it is not symmetrical about its point of inflection. Gompertz curve implies a linear relation between the relative growth rate and log y, relative growth rate and time. The Gompertz model. The Gompertz curve describes a trend in which the growth increment of the logarithms are declining by a constant percentage. Thus, the natural value of the trend would show a declining ratio of increment, but the ratio does not decrease by either a constant amount or a constant percentage. A general equation for the Gompertz model is log y is equal to log a plus log b into c to the power t. The Gompertz and logistic curves are similar in that they both can be used to describe an increasing series which is increasing by a decreasing percentage of growth, or a decreasing series which is decreasing by a decreasing percent of declines. They differ in that the Gompertz curve involves a constant ratio of successive first differences of the log y values, while the logistic curve entails a constant ratio of successive first differences of 1 by y values. It is a log-log model. It is often referred to as a double log model. It is represented as y is equal to at to the power b. Sometimes it is also represented as y is equal to a plus bt to the power gamma, for gamma is equal to 1. The other equally well-known model is Ware's model. Ware's model is represented as y is equal to delta 1 minus omega to the power minus t, where delta and omega are greater than 1. Use an exponential model if the approximate trend when plotted on semi-logarithmic paper is a straight line, or if the first difference of the logarithms are constant. Use a logistic model if the first difference resembles a normal frequency curve, or if the first difference of reciprocals are changing by a constant percentage, or if the approximate trend value, that is the original data, when expressed as percentage of a selected asymptote, appear linear on arithmetic probability paper. Use Gompert's model if the first differences resembles a skewed frequency curve, or if the first differences of logarithms are changing by a constant percentage. Growth models can be classified using two growth functions, alpha 1 and alpha 2, where alpha 1 is equal to y to the base t plus 1 divided by y to the base t, and alpha 2 is equal to y to the base 2t divided by y to the base t. Alpha 1 is called the first growth function and alpha 2 is called the second growth function. The theoretical relationship between alpha 1 and alpha 2 has been worked out to be alpha to the base 2 into t is equal to alpha to the base 1 2t minus 1 into alpha to the base 1 2t minus 2, so on up to alpha to the base 1 into t. According to Eghe and Rao, the method of determining the growth goes back to the intrinsic growth rate properties of the data for a good understanding of what is really going on. The authors have really suggested that in order to get a simple clue for the selection of the best model, the plot of two growth functions for different mathematical models, namely exponential, power, linear, logistic, and Gompert's, are presented and visualized in terms of the simple classification type 1 for increasing, type 2 for constant, type 3 for decreasing, and type 4 for increasing and decreasing. Obsolete means to be out of date or no longer in use. The process of being obsolete is known as obsolescence. This term was first used by Gross and Gross in 1927 when they analyzed the references in the Journal of Chemical Literature in the year 1926. They observed that the number of references falls to 1/2 in 15 years. This is a characteristic of S&T literature, generally measured in terms of half-life, defined as the time during which 1/2 of all the currently active literature published. Time needed to account for one half of all the citations received by a group of publications. Discussed in the context of diachronous studies, the use of particular items through successive observations at different points in time. Synchronous studies are concerned with plotting the age distribution of material used at one point in time, median age of references at time t. If growth rates of literature and contributors are equal, then the obsolescence rate remains constant. The higher the growth rate, higher the obsolescence rate, quicker the obsolescence and half-life. Scientometric techniques have evolved over time and are continuing to do so. The counting of papers with attribution by country, by institution, and by author, the counting of citations to measure the impact of published work on the scientific community, the counting of co-citation, which is the number of two papers cited together in a single paper. All of these techniques combine to give more detailed and a more effective measurement.